what left yesterday. So yesterday we finished a discussion of how to rehab most concrete structures, and we continue here with the steel members. Steel structures usually is relatively easy because like when concrete deteriorates, it's actually, especially the timber structure, when they deteriorate, the quality gets worse and worse. But for steel, actually, the quality does not change. What is changing is the section. You may have collisions, you may lose some sections. So it's very, very easily to be quantified. You can take some measurement to see how much section is lost. So by that, you will be able to calculate what will be the remaining capacity. So for that reason, a lot of time when people decide to design for a certain period of time for them, especially for foundation, like for pile, if you drive a steel piles down, and you have no way to maintain that, and you just do some soil chemistry tests to see how corrosive they are, and experts may be able to tell you like how fast the corrosion may be for that kind of environment, and then all you can do is just calculate how much corrosion will be in, like for example, 75 years, and you just design a structure which is a little bit thicker than required, and to compensate for that corrosion. So and that's why for steel members, usually it's very straightforward, and also how to rehab is also very straightforward. You just add more sections back to what's lost. But there's one particular concern for steel structure is fatigue. Fatigue was not very well known until 1970s. So a lot of bridges designed before that, actually in the United States, almost half of current bridges designed before that. So at that time, people did not have a lot of knowledge of fatigue, so that a lot of bridge has been experiencing fatigue problems. So we'll have a section actually to discuss fatigue issues. As I said, steel corrosion is relatively easy to be spotted. So, but that corrosion, typically there are two types of corrosions. One is weathering related, like it's surface corrosion, which means it's very easy. You see a lot of rust, you will be able to see, like for example, in that case, and the corrosion, I show this picture that like in this case, you will see like layers of rust. When you see layers of rust, it means it's a studied lost sections. But in this case, actually, you may still consider it as very minimum section losses. But in this case, probably it's time to do a repainting. In other words, you may remove the paint has failed, so you just do repainting. And that type of corrosion is we call it pitting corrosion. Pitting corrosion is typically caused by chemical reactions in this environment, especially in a coastal environment. A lot of birds, when birds, they may have like bird drip, that causes corrosion, and also corrosion by like leakages of bridge, like through expansion joints or through other means. So that causes chemical reaction. This kind of corrosion typically is very localized, but usually it's very deep. In other words, that corrosion really creates section losses. Like for example, that connection plate is heavily corroded. So actually, when we did a bridge inspection and we found something like that, we usually will report to a bridge owner saying that is something we may need to address that very quickly. And actually, for that particular bridge, it's a truss bridge. It has two lanes of traffic. And so the bridge owner says, okay, maybe you guys just do some design, we can replace that. And this is just like two channel sections. This is bottom chord of a truss and has two channel sections. So they have 4 plates, connection plates to connect that. So what we did was we did some calculation. We said like, if we take 2 plates out and leave another 2, if that can be able to carry the load. Of course, it won't be able to carry full load. So then we calculate like how much, if that can carry that load by itself. And it was okay. And then we calculate basically if we just shut down one lane of traffic near that truss and to see if that can be carried. And we found actually that that 2 plates can be will be able to carry just one lane of traffic. So in that case, we did not have to shut down the bridge. So we just replaced like 1 plate at a time. Although we would replace 1 plate at a time, we always assume, because it's become asymmetrical, we assume 2 plates will be lost at any particular time. And of course, usually when you deal with that, you don't take any chance, because during construction, a lot of things may happen. So in that case, usually we will have to provide temporarily, like what we did, we provide a cable to connect this truss joint to the adjacent another joint. Just cable, it's not very, very tight, but it's just tight enough in case that if something totally dysfunctioned here, or it means it's broken here, that cable will be able to carry the load. Another thing we see a lot recently is a lot of bridges hit by like traffic underneath. Usually, of course, this will be done by accident inspection. Usually, in this case, definitely you may say, okay, you may not need to shut down the whole bridge, but you need to shut down one lane of traffic. Usually they will put, on the top, they will put concrete barriers on top to block one lane. And to do the repair, there are 2 ways. One is you can simply just replace the girder with new girders. That takes a little bit of time, and to do that, actually, you may also have to cut the deck out, because you cannot put the new girder, because new girder has like shear studs connecting deck. So that may take like a month or something for the construction, and you also have to wait for probably a month for the fabrication of a girder. So in other words, it may take like 2-3 months before you can complete. And that's like in this case, actually, probably just replace girder is a best option. But if the girder were not damaged that severely, the contractor could just apply very, use a very hot, almost like a welding equipment, like a gas type of thing. They just make it really, really hot. And once the steel becomes hot, it becomes soft. You can bend it back to original shape. And some people don't like that idea. The reason is that once you re-hot the steel and let it cool down, effectively you change the yield stress. It may not change the ultimate stress, but yield point may change. So they may not behave as like the original design. But on the other hand, because they have they have a lot of redundancies. In other words, it does not really matter whether it yield first or later. Once a girder yield, it will not carry additional load, so the adjacent girder always takes over for any additional load. So I personally don't care too much about that change of yields. Of course, it will definitely change the ductility of the girdle. In other words, it may cause a problem in the future for fatigue issues. Like for example, if this has like a cover plate, so that may become an issue. And another thing is typically for steel girdles, like a lot of older bridges, especially like railway bridges, they have like only like 2 girdles. That's what we call fracture critical members. And if you have like these multiple girdles, it has a lot of redundancies. We call it non-fracture critical. So when you do inspection, usually you need to identify. There will be a special inspection for this type of structure. Actually, I heard that there's a bridge collapse yesterday or today. And that bridge was just like a seam has only two girdles, no redundancy. Another very critical element is called I-bar. The reason I-bar is very critical is that I-bar typically has a connection like that, and most used for truss bridges. And they don't usually have redundancies. So when I-bar fails, the whole truss fails. And the I-bar was made like by casting one member like this and cast another member like that. Then the forge operation, like they put that member and that member in oven, and then it's really, really hot, like red hot. Then they will put them together and use like hammers to knock, and after that it's become one piece. But like this is the same process. But that process does not really create a monolithic elements, so that there's always like a micro crack inside. So because of these two reasons, one is no redundancy, another is original defect. So that's why these kind of elements usually need to be really, really carefully inspected. And of course, we don't design this kind of thing anymore. And another, the U-bar. U-bar pretty much just a bar, like a bolt, U-bolt. And they just, the same thing, they put them into very hot oven, and then just when it's soft, they bend into U shape. By bending that, it creates a lot of cracks. So this type of that's the Silver's bridge which collapsed in West Virginia, which was very classic examples of how like a U-bar and non-redundancy cause collapse. Not U-bars, I-bars. Fatigue, as I said, fatigue detection is very, very essential. So typically when we do an inspection, like for normal inspectors to do inspection, you don't have very, very specialized tools. And what you can do is dye pinch. Dye pinch is like a spray. It's like orange color. Once you spray it, if the liquid will see a crack. If there's any crack, it goes into, and you will see the crack very easily. And of course, not all fatigue crack is on surface. That's a problem. If it's on surface, you will be able to detect that. And if it's not on surface, you cannot detect with dye penetrate or like visual inspections. And so you may use it like a X-ray or gamma ray to detect. Another relatively cheap alternative is eddy current and magnetic field. Eddy current it's not very accurate. It's very inexpensive, but people don't use much. Magnetic field is very, very accurate, but it's very useful for inspecting like mechanical components. Like for example, manufacturers, if they manufacture a component, they can put it on the table and spray iron sand. Then we apply a magnetic field. So if there's a magnetic field will go through this steel, and if there's discontinuity, like a crack, then there will be disturbance of this magnetic field that will cause the ion sand to bump up, so you will see that. But for bridges, typical bridge elements, like in a vertical or like for bridge elements, like, it's very difficult to actually do magnetic field, although it's simple. So a lot of people use ultrasound tools, and that's is most common tools. And it's not very accurate. The most accurate will be X-ray type of thing. It will give you actually very quantified information. All these only give you some indication if there's potential cracks. Yeah, these are some examples. And you can do visual inspection. If you have crack, usually the crack will break the painting, so that it may cause rust. So you may see a rust stain, and that's a crack. And of course, you can do a visual inspection. But to do visual inspection, the crack has to be very, very significant. And sometimes you cannot really see visually. You may just use dye penetrate, it will spray these orange colors, and you will see that. And actually, if you have a ultraviolet light, I don't know if you go to if you travel through airport, sometimes, especially in the United States, people use driver's license as ID to detect if your driver's license is authentic or not. The inspector uses ultraviolet light, and that they can do that. It's the same thing. So that will give a very, very vivid signs of any crack. Radiographic is relatively simple. It can detect internal crack. What you do is you have to basically just a receiver and emission of radio active rays. And so when they travel that, if there's a cavity or crack or something, it will show it. Just like taking a picture. It's just opposite, black become white, white become black. Eddy current, as I said, it's a very, very cheap instrument. It can detect some kind of a crack, but not very accurate. And magnetic field should be very accurate if you have ways of applying it. If you can bring something to your laboratory, you can do that very, very well. But at site, especially at vertical web, it's difficult. Some people using some kind of little bit wet sand, ion sand, but that is still not working very well. Ultrasonic is a relatively inexpensive. The instrument costs probably about $8,000 to $10,000, and it can detect signs. Usually, what people do is you use these to detect to give some kind of indication if there's a problem. If you really feel like there's a problem, then you use X-ray to quantify the problem. Basically, just as a screening process. And weathering steel, I don't know, is weathering still popular here? Yeah, probably it's not very good for coastal environment. Weathering steel actually was invented by railway companies, and actually because railway companies do when they ship a mine, and they always scratch their paint, so they may say, okay, maybe we can do some research to find a kind of steel that we don't need to paint it, so we don't care about scratching. So it's the same concept as we know aluminum. Actually, aluminum is more chemically active than steel, but when aluminum rusts or corrodes, basically oxidize, it forms a very, very dense film to prevent further corrosion. So weathering steel is the same concept. It just let it corrode, but the rust, corrosion is so dense that prevent further corrosion, and so that protect. In other words, you don't need to do any painting. But the problem is that only prevent corrosion for non-chemical attacks. In other words, if it's just like a normal work, like a moisture and normal condition, then that's perfect. But if you have a salt or any chemical attack, it will not work. Like for example, actually when you do inspection, a lot of people ask me, they say, how do I do inspection for weathering steel? Because they're meant to be rusted. I say you've never done. Once you've done the inspection, you will not ask that question, because like weathering steel is that steel is very dense, very uniform. Actually, if you use like hand to scratch that, you don't see any rust on your hand. It's very, very dense. But if you see it like discoloring, then that means these are really good rust. These are just rust caused by chemical attack. Like in this case, it's caused by leakage of water. When water leaks from bridge deck, typically they have a salt, because most bridge has a salt in the winter. So that's why they call so. So for that reason, usually when people design bridges, if there's expansion joint, they will paint these for about 3 meters, just to make sure that when the water leaks, that won't cause corrosion. Again, typically, when you deal with steel members, typically you only address that when you do the deck replacement. Like if you simply do a deck overlay, that kind of operation, probably you cannot do much about the steel members. The only thing you can do is a repainting. But once you do the deck replacement, then you can do a lot of things. Typically, what I always do is that I always, of course, you normally would do a repainting, but I usually just wear shear studs to make them composite. Even if you have sufficient capacity, you still do it, because shear stud does not cost much money. But once you do the composite deck, the efficiency, the stretch efficiency is much higher. In other words, you may actually increase, sometimes you may even double your capacity. So, although you may not need that much, but extra capacity is always a good thing to have with very little cost. Another thing I typically would do is that I will make, because old bridges, especially bridges designed in the 1940s, 50s to 60s, and they always design simply supported. I don't know why. Maybe because at that time people did not have computers, who they didn't want to do a lot of structure analysis. So simply supported will be very, very easy to calculate. But nowadays we always try to design continuous structure as much as we can. But we can make them continuous. Once you make them continuous, you eliminate the expansion joints, and also you increase your load capacity very significantly. There's many options to make them continuous. One way to make them continuous is just treat that as a splice. If you treat that as splice, you just make them continuous on top flange, by bottom flange, and the web. But this is very, very tedious operation. So especially the bottom flange, because bottom flange has support. In order to do that, you have to provide temporary support here and here to do that. So it's very, very tedious operation. So this was very, very at early stage, because at early stage people say, yeah, make them continuous, just make them continuous. And we don't do that as much as before. So option 2 is relatively simple. It just make them continuous, like mainly through top, from tension side, you make them continuous through the deck, and you provide like a little bit steel on connections on the top flange, but the bottom flange, like since they were bearing here, so you cannot add any plates easily. So what you do is just you just build a steel to against somewhere here, so that the compression will be resisted by these like steel connections here, and tension will be resisted by mainly the reinforcement in the deck. Of course, these will be steel plates will be used for only casting concrete deck. When you're casting concrete deck, there will be a tension here, so that will resist. For after that, the rest will be resisted by these. But these are another approach. So this approach will also make when you're casting concrete deck, it's almost like a continuous span when you're casting concrete deck. And the third option is actually the most popular option. Third option is that really you don't need to have any connections, either top or bottom. So what I do is that I can build a concrete diaphragm all the way from one side of bridge to other side of bridge, so that then I just cast concrete deck. So in other words, when you cast new concrete deck, it's non-composite, it's still simply supported. But once the deck is cast, it's become continuous for live load. This is the same approach for most, like a precast concrete girder bridge. When you do the new construction, you do a similar fashion. You just put girders and the cast deck. And when you cast deck, it's non-composite, but after casting, it's composite. So all the compression force will be resisted by these diaphragms. So you just punch some holes in these girders and let reinforcement go through. For some holes, you have reinforcement for a diaphragm, which is similar in this case. This will be like original pier bend, and this will be new diaphragm and the new deck. Again, also just like a reinforced concrete, if a steel member is insufficient and the deck is okay, like if you don't replace the deck, you still can provide reinforcement increase by adding post-tension rods. You basically just bolt this bracket, and then you post-tension so that can enhance the bending capacity. Truss members usually it's relatively simple when you do the calculations, but it's a lot more complex if you want to do a replacement. So construction-wise, it's very complex. Design-wise, very simple. Again, that one we just discussed earlier. And typically, as I said, for truss members or any steel members, because what you see is what you get. So if you lost some sections, you can always add some sections back. Like for example, you can if you lost section, you can just bolt two pieces of channels, Or sometimes, if it is really dependent, if it's compression or tension member. If it's just a simple tension member, you might just simply bolt the two pieces of steel plates will be good enough. Just one thing I probably need to mention that whenever you do a rehabilitation or repair of steel members, try not to do a welding outside. Because welding outside is very, very difficult to control the quality. So it's always better to have anything like bolted. Yeah, this is another thing, actually another bridge. I think it was in West Virginia. Actually, for any bridges, of course, rehabilitation is always one of the steps you may have to face at some time. But routine maintenance is also very essential. I always recommend that for every bridge you need to, especially in the north, they have snows in the winter and then spring comes. So I always recommend that when the spring comes, they use a power wash to wash the deck of drainage and steel members, expansion joints, bearings, and if you don't do that, that's what happens. These are a debris just accumulate that side. Actually, it's always wet because, and our inspector there, and the inspector took that out, and we saw that the corrosion is so severe, almost half of the section is lost. So that in that case, we just call the bridge. They're the same bridge as we discussed the splice. And they have actually it's only about 1 kilometer apart. So that bridge had the emergency repairs, but this was not as simple as the last one. Last one just splice plates. So this is a major connection. So this bridge was actually shut down for the whole replacement, whole repair of these members. So that's why routine maintenance is very, very essential. It should be always part of the strategy for the asset management. A cassette plate is also very important element. And whenever you see these kind of things, there's no if something can be replaced, you just replace them. So you don't need to repair. Only if something cannot be replaced easily, you'll try to strengthen it or modify it. Yeah, as I said, power wash structure is, especially for steel structure, is very essential. That cause especially in the region where you use salt in the winter. A truss member strengthening, as I said, there's a lot of ways. A lot of truss bridges made of this section. They're also channel, basically 2 channels, and they have a lot of bars to connect them. And in that case, if this member were deficient, what you can do is you can just instead of you can replace these with plates. Once you do that, it becomes a box section, and that can be also used for a I section. If you have an I section, you can also weld 2 plates to make them a box section, similar to that type. Yeah, there's an example of a truss bridge. Sometimes the truss bridge member is so small that it needs to be replaced. To replace the truss member is a very, very difficult operation. The reason is that, and when you take one member off of a structure, you have to release the stress. If you don't release the stress, then it will have a big it will have a big action when you shear off the rivers or if you take off the bolts. And to do that, actually, it's very, very difficult. There's no ways to test what stress is in the steel. For actually concrete, actually, there's instrument that I mentioned yesterday. They have a steel thing, like a bolted to it, and they cut. They have a saw cut. Once the saw cut, that steel thing actually had automatically detect the stress of at edge, so that additional stress can be calculated back to see how much steel member is. But for steel member, because steel member itself is very small, so there's no way. All you can do is do calculations, and you do the best calculation and predict what the forces should be inside. And usually, these type of structures, the truss structures, are typically has no redundancy, so that the calculation usually is very straightforward. Another thing, you need to make sure that you want to release the stress, so that if you want to replace one member, you need to jack it to. Okay. And these are actually the jacking force against the joint, and actually these are the temporary members, so to replace the original member. And another very essential thing people always have to keep in mind is that whenever you do a rehabilitation or repair, even like for simple bearing replacement, try not to rely on the jack to sustain the load. Like for example, if you want to replace the bearing, you jack it up, and you should put something like a permanent to keep the structure up. Like for example, shin plates, and then do a replacement. Because the jack itself is not very stable. Sometimes if the oil leaks or if the power is off, then it may just get back. But for this, like for bridge replacement, definitely you don't rely on the jack. So that's why they have like temporary members to hold the structure, and before they put the new members back. Like these are temporary structures. That's a Marine Parkway Bridge in New York City. And so they did a bottom core replacement for all the trusses. And these are basically some pictures during operation. They brought a barge. A barge is very important. So once you have a barge side by side, you can have like heavy equipment sitting on the barge, and also you can have resting areas and like temporary toilet, lunch areas, and staging area. Material can be shipped to the barge. A cable hanger inspection. Cable hanger inspection, there are two ways. One is they have automatic, like a robot type of thing. Actually, it travels by itself. It's powered, it's battery powered. So it travels like through one of these cables, and it uses like a magnetic sensor. It can detect any breakages of these cables. And if you don't have that, traditionally, people use a vibration. Like the vibration frequency is a function of the length of cable and the section of cable. So you can calculate the frequency, and you can test the frequency to see if they match. And if the frequency does not match, the calculated probably something may go wrong. But the sensitivity is not very good, because the boundary condition of these is not mathematically ideal, like when you do the calculations. So that's why vibration testing is not very sensitive. But that thing is very sensitive. They say they can, if there's any one strain broken, it can detect. Timber bridges. I don't know do you have a lot of timber bridges here? You don't have. Actually, in Maryland is like almost like half a state is on a swamp. We call Chesapeake Bay. So over there, to build bridge very cheaply, what they did was they don't need to do any foundation. They just drive piles. Like this pile was driven, and just that pile is a foundation and also pier. So they put like timber deck on top. We have a lot of such bridges, and we found that the timber inspection is like very, very difficult. What we did, we use hammers to knock, just like concrete. If it's very, very solid sound, it's okay. If it's like a very, very like a soft sound, then you know it's a problem. And usually you have to go to do the inspection. We find like if the timber is permanently dry, usually it's okay. And if it's permanently submerged in the water, it's okay. It's always like a tide range that cause problem. Like it's dry, wet every day. And so that's why when you go to do the inspection, make sure that the tide water is at low point, so you will be able to see the problem. And sometimes you're not sure, like you really cannot sure, because sometimes the timber is good, but it's wet. It's still like a little bit soft. What you do is you just use a drill, just like a regular drill, a drill hole. You can feel like if it's very solid, it's hard to drill in. Like if it's soft, it just get in very quickly. Yeah, that he's doing like drilling. So to repair is relatively easy because, and basically you just use a steel plate to replace that. In other words, you don't have to remove the deteriorated. It just puts steel plates to replace them, so that these steel plates will have sufficient capacity. And we designed like the standard. Like if you have 3 pieces, it's very much, because timber size are not always the same size. So if you have 3 pieces, you can always bolt them to fit. Foundation inspection is extremely difficult. That's why we don't usually perform unless there's indication. Like if there's indication there's like settlement or rotation or something, then you may have to deal with that. Basically, one way you need to know is that like sometimes the bridge owners say, okay, I need to replace superstructure, but my substructure is okay. I want to keep. And but they don't have any design drawings or design document, and you don't know what kind of foundation they have. So what you can do is that there is a very like simple instrument. It's just an impulse response. Like it basically just knock it, and once you knock it, it create a like sound wave. So the sound wave will travel down, and once it travel down until to the end of concrete. So some may continue travel into soil, but some may bounce back. And once bounce back, that sensor will receive the sound bounce back. And because the sound wave travel in the concrete, the speed is something we know. So that by detecting the time we knock and time we receive the bounce back, the computer will automatically detect how deep your foundations are. And of course, you can do another thing, like you can just drill a borehole. If you drill a borehole, you can do is you put a sensor, instead of sensor put here, you just lower the sensor, you knock it, and lower sensor, you receive it, and you go down, you keep on going down, and until you go further down and you knock it, you don't, you got a sensor, and like every time you just have one point, when you keep on going down, you just put dots in a paper, so there should be a linear dots. And after that, if you go further down, so that will change the angle. So you may have dots, 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 and it's change angle. Once you change angle, you just measure how long your strips are, and then you'll be able to tell how deep that foundation is. And another is a very, very similar approach. You just drill a borehole instead of using waves and sonic sensors. You use the radar sensors. So you just put that into hole, and that will emit a radar signal, and it bounces back. And you go further down, bounce back, and go further down, bounce back, and go further down, and it does not bounce back. And then you just measure how long that is. Sorry. Yeah, and for the apartment, as I said, typically the problem is rotation. And so if your footing is not sufficiently designed, the soil here will push that and create a rotation. So if they see this kind of problem, most likely it's caused by that. And the wing wall has similar situation, like it may have a rotation problem. So to address that, typically what you can do is just provide tie back. Tie back, you can actually provide like a pre-stress force. Sometimes you can push back a little bit to collect that. It may not go back like perfectly vertical, but it can actually at least stabilize it. Like the tie back. Tie back has different design and different materials. Typically, it really depends on how old your structure. If your structure is very, very old, only lasts for another 10, 15 years, you may not need very, very good corrosion protections. If the structure is relatively new, you want to keep for 50 years, you may choose better corrosion protections. Like tie back, I don't know if anybody use. Tie back is like that. First you just drill a hole. Once you drill a hole, then you insert the rod. It's basically just a single rod, but they have a spring. There's spring at near the head. That spring is surrounded by the rod, so the rod will not be able to fall down. If you don't have a spring, the rod will just go down to the bottom. So of course that keep that rod in the center of the hole, and then you just grout it. They also provide a pump the grout, so grout certain portion. If it's soil, usually need a larger grout. If it's a rock, usually it's relatively easy. So like for these, typically we use performance-based. In other words, you don't tell a contractor what type of to use. I mean the size or how much grout. You just tell them what force I need. So after you're doing that, you do a test, because you are doing actually pre-tensioning. So of course, if they don't meet the design requirement, you may just pull out, and you have to do that again. And another, like if it's a very small bridge, you may be able to use like a called jack pier. Jack pier is very much just like a pipe. This pipe typically is like a screw type of pipe. You just screw down, and then what you do is that you can actually provide some little bit excavation under the footing. So they have a bracket here, and then in the bracket you can put a small jack to jack a little bit up to seal the crack. And these will become permanent. Micropile is most widely used for strengthening your foundation. Like if you have spray footing and the footing is not sufficient, what you can do is just using micropile. Micropile typically just drill a hole and grout, provide like a concrete type of grouting material, and usually there was one bar inside. And you can do like this, and or you can make it folding bigger and put the piles outside, the original folding like outside, either way. But the key element is like if you do this, make sure that it has to be very rough, usually rough connection, so that when a load comes, it will not like penetrate into that. This micropile, like equipment very, very small. Like it can, it can be done like under the superstructure, because usually you have a bridge deck here, or it can be done for buildings. Like this is one application for a building. Like the building, they have like small footings. The footing is too small to sustain the additional load, to sustain load. So what they did was they provide like a micropiles from outside and put the concrete around it. And that's another bridge. That's a bridge with timber piles. The problem with timber piles is that the timber deteriorates over time. So after a long time, and you feel like the timber is no longer working, and you don't have to take the timber piles out. You just assume it's gone. What you do is you can just provide, provide micropiles to replace these timbers. So you just calculate how much load you need, and the contractor will provide micropiles to get that kind of loading. Again, like these are at footing, usually you use like a globe, like screw type of globe, so that when the concrete casts here, it has a very like good bonding or friction resistance. Another thing people may do is that we call it like underpinning. Underpinning is like the concept is like if you have a if this is my apartment, and I don't have sufficient capacity now. So what you can do is that you can just come here. I come here. I just dig a small hole. So I go digging down until to the bottom footing and digging into the footing. Of course, you may lose a little bit support, but what if we shut down the bridge? There's not much load. By removing a little bit soil underneath the bridge, it will not be an issue. And once you go to inside, under the footing, you're digging further down, and until you dig into very solid soil or rock, and then you just cast concrete all the way up to support this point. And now this is on deep foundation. You just go to somewhere else, like maybe like 10 meters or 8 meters away, you do the same thing. And once that, you will have a couple of big piles to support the current footing. And then you just provide beams to connect these newly built concrete piers, so that the whole structure is supported by these large piers. Like first you just dig it down, and you dig into these. So but to prevent the soil from collapsing, every time you dig, you need to add the timbers. Just keep on adding timbers from each side. So only one side is open. So you dig into that, then you dig further down it dig further down, and until you reach the desirable soil or rock, and they just build that. And after that, you can typically people put 2 channels together and to support existing footing. After that, it's become a deep foundation. Another footing improvement is jet grout. Some people call soil crate. What it does is that, like for example, if you build a bridge pier here. And later that pier settles. You may say, oh, I wish I should build a footing here. This is really good soil. This is not very good soil. And now it's too late. What you can do is that you just drill a small hole. Basically, you just try to modify the soil underneath. So that you don't have to make that a solid concrete. As long as you can modify the soil, which is strong enough, so that effectively you will become a footing sitting on this layer of soil. So that's why we call soilcrete. So what it does is just drill a hole through your footing, go down to your desirable level, and then it will retreat gradually. While retreating, it rotates very fast and inject like simultaneous materials. If the soil is very granular, like a sandy soil, but if the soil is very silty, it will also inject a lot of air. The air will be injected first to basically break down your soil structure, and then it has if it's very granular, it just do that. It's just when you retreat, it inject growth, so that create that. If it's a very silty material, it actually has air coming out to basically just break down your soil, so that otherwise, if it's too silty, the growth may not be able to travel far enough to form these. And these are the specifications. And so these are the applications. Again, for this type of application, typically we use so-called performance-based specification. You don't tell them like what diameter you should use. The contractor will decide whether you use small, many of these, or using larger, bigger ones. As long as they give you the performance, what load to be used, and what level of foundation you need that to be. And that is chemical growth. Chemical growth, again, there's hundreds of different definitions of chemical growth depending on application. And the first application of chemical growth was used for leakage seal. Like if you have tunnels and when leaks, there's no way to repair from other side. People use inject chemicals. Typically, it's like epoxy-based chemical which will expand to seal the crack. But here, this is for use to reinforce the soil. And basically, it's the same. Like for example, if you have we have a newly built bridge, and bridge was on timber piles. But these piles are friction piles. So we all know that friction piles, it's very difficult to estimate the capacity. For bearing piles, if you have very, very good rock, soil, and a bearing on that, typically the capacity is my pile capacity. But for friction, it's difficult. So after the construction, they found the whole bridge is gradually setting. So they say, well, we should have bearing piles. So what you can do is that you just inject a chemical growth. Basically, just make that piece of soil, actually sand, into a big piece of rock. So after making that big piece of rock, then these piles are basically just become a bearing piles. So they will not be able to settle much. A chemical growth also used in application in Boston. Boston, the whole city is built on beach. Actually, if you dig out, it's all sand. So if you want to build a tunnel, if you tunnel through sand, it will collapse. So even if you have open cut, it won't work. It will collapse. So how they did was they inject the chemical grout like along the tunneling route to make it a like big piece of rock. It's not like a very solid rock. It's very soft rock, but it can sustain by itself. And then the tunnel can cooling through. It's the same thing like for I worked for like oil piping companies for design their piping lines. Typically, they put the oil pipe in the ocean so that they don't have to buy land. but later, the pipe has to go to land. But to go to land, they don't want to put on the surface because people may damage it. So they still want to put it underground. They put it underground, but to go from ocean to land, there's beach. So if they dig on the beach, it will never work. They keep on digging, they will keep on collapsing. They do the same thing. They just using chemical grout to make the sand become a sandstorm, very soft storm, so they can dig a trench. Underwater inspection repair. Underwater, typically using divers, but there's also underwater sonar, and for very large inspections. But for regular inspections, we typically use divers. To use diver to do inspection here is relatively easy, or even in Florida, but water very clean. If you do an inspection in Maryland is Chesapeake Bay. It's almost very muddy. You cannot see anything, so you have to use a hand to feel. So for underwater inspection, basically just to inspect two things. One is the structure itself, just make sure that the foundation, the pier has no spotting, no cracking, that kind of thing. Another important is inspect the footing to see if there are scar damages or undermining. Typically, where you have hammers. All inspectors always bring hammers for variety of reasons. And they also have video cameras. And typically you have to do inspection for everyone. And you do normal inspection, they have to inspect everyone very quickly, but they have to inspect about 10 to 20% very detailedly. And if you see a footing have a scar damages, you want to take picture. Typically, you put a tape so people can see the magnitude. Otherwise, it's difficult to detect. That's in Maryland, really difficult to see anything. So that's a really challenge. These areas, you can actually have really good pictures. You can actually see. Again, when you do the inspection, make sure that you do the inspection at the low tide. When the water is very low, so most area will be exposed. Foundation actually scar this scar damage is actually I think the number 2 reason bridge collapse in the United States. And number 1 is related to fatigue. So that's why, and when we if you see these are after major storm, the bridge is still standing. The reason the bridge is still standing because they use deep foundations, and that's why when I design bridges, I never design spray footing anywhere near the water, unless the riverbed is very solid rock. In that case, you can build a footing. It's cut into the rock a little bit. You can put. If it's just a soil, you don't do that. And the challenge is that if the rock is very deep, you can drive piles. But if the rock is very shallow, for example, about less than 10 meters deep, And you cannot drive piles. If you drive piles, because you only have like 10 meters of soil, so when a storm comes and if they wash out these soils, then the bridge still will not be stable, may still collapse, because the pile is typically like pin. It's considered pin in footing and pin at bottom. So in that case, what you can do is you can use like caissons as a foundation. Or if you do want to use piles, you just drill a hole into the rock and just put the piles. You don't need to drive the piles. Just put piles in the hole and grow the bottom portion into rock, so it's become a fixed connection at the bottom. So even if that happens, it will still be stable. And whenever I design bridges over the stream, I try to eliminate any foundations, because building foundation in water is very expensive in the first place, and also it's very difficult to maintain. And especially in the north, the water is not, like high water is not caused by rain. Like in the south here, the high water is because when you have a hurricane or something, there's big storms, so that's giving high water. Over there is like, they have whole winter of snow. Every day have, like not every day, like have snow. The snow never melts, it just keep accumulate. They have a lot of snow in the mountain. And when the spring comes, they all melt. So that's what they give them like the highest water, where the water is. And that's when it comes, and then if you have like tree branches, debris, they broke that out. So that gives them a big accumulation of water. So that causes a lot of damages. So that's why I try to avoid building any foundation in the water in the first place. And score inspection is like after major storm, you just inspect, like for example, if you have a deep foundation, so you have a scars, so it may take some time to repair. It's not some kind of emergency. Like only if you have a spray footing, like if you have a spray footing and you find a scar hole, that become an emergency. You may have to repair immediately. And typically, a foundation scar protection is using riprap, like big stones. And sometimes big stones difficult to get. And I always use like a concrete bag. Basically, just big piece of concrete bag. You just put it in the water, and once it's wet, it becomes a big piece of concrete. So they can lay it down very nicely. Yeah, like that. And once you have a hole inside, so what you typically do is you just pump the concrete into that. Usually, like every a meter and then 1.5 meters, you have about that size pipe, and you just pump from one pipe. And the water may come out from other pipes, and then you will see once the concrete grouting material come out, they just do from there and keep on going. Of course, this grouting material may not be in very good condition after doing that, because it's so wet, there's a lot of waters. But because you're only replacing the cavity with material that always better than the soil before. So they should be sufficiently straight, good. But after that, real thing is the protection. You just keep that concrete bags or riprap stone protect, so the next storm comes, will not be able to compromise that. Yeah, we'll have actual case studies for scar damage. Like this is sometimes even if you don't have any damages, and you may do a protection, you just put like a concrete bags over there just to protect for the protection. Like if sometimes when a channel is very narrow for a very small bridge, you might put like a concrete bags for the whole channel. And actually we did that a lot, but later we found it's like if you do these, the fish may have trouble to swim because it's very smooth. So that's why people still prefer like a rock. Because when you have a big rock, they have a lot of refuge areas to rest. And for the piers, you may also do some kind of repair. Instead of having that, you may have pipes from both sides. So pier is easy to repair than the abutment. So we have brick at 10, right? Or 10, 14. And these are typical specifications or notes for repair. I did a lot of scot damage repairs. So that's why I developed standard notes. So basically, these notes will be used for a contractor to do a repair. I think the reason we had a lot of scot damages in Maryland was because, as I explained yesterday, before it was like a rural area, most of like farmland and forest, and now it's become an urban area. Like we built a lot of buildings and highways and basically just parking lots and so everything. Before when the rain comes, they just penetrate into ground. Now it all becomes surface water. So surface water all go to the rivers very quickly and make the water much larger. And that's why we don't have much historic data anymore in Maryland. Like here, basically you may have very accurate, like 10-year storm, 100-year storm, and so on. And another actually very efficient way of protection is using sheet piles. But sheet piles has a problem, like if your bridge is not tall enough, you don't have a room to drive sheet piles. So only for like a very large bridge, the bridge is very high, you may bring a barge and drive sheet piles. The sheet piles provide very, very good protection. If you have sheet piles, then you just pump grout into these cavities and then put a riprap on each side, and after that they just cut off. And these are the pictures like before and after. I think the problem with these bridges that the original designer did not do any calculation when they specified, they did not specify the size of rock. So the size of rock should be calculated based on the water velocity, like your highest velocity for like a 100-year storm or 200-year storm. So that's why, because it's too small, just even these rocks being washed away, and the largest storm. Another thing we typically do is that in the ocean environment, because the water is very water is salty, so that is very corrosive. So no matter whether you have a steel structure, concrete structure, or timber structure, they all get damaged easily. So there's a company in Baltimore, Maryland, they called F.ASCE Industry. So they produce a lot of repair materials. Like basically, they develop a plastic foam. I will show you next one. So basically, they produce plastic foam, which is customer designed based on your actual member size. So they have a key at each. They can open up and the key in become these. And this is typically about 75 millimeter gap from each side, and then you just and also if you have deteriorated concrete, you remove deteriorated concrete, and then you seal the bottom, so you can just they have a special repair material. It's very liquid. It's like self-leveling. You don't need to vibrate. it just pour down, and you see at the bottom. So after that, the form will be permanent form, and the repair will be done. It can also be used for like circular column, the same, whether circular, rectangular, square. And of course, you don't have to do that. You can do like a regular repair. Like sometimes you may just have a repair with like a reinforced concrete. Like for example, if you have a steel pier and that's not sufficient, you can just provide like any form, either like a carbon form or any form, and provide reinforced concrete. Typically, we call it reinforced concrete jacketing for steel. So that jacketing is also like be able to protect these members from corrosion. Again, typically the range of these is like if the low tile, that's low tile and that's high tile. So it just extend from both sides so that the member, if it's permanently in water or permanently dry, should not have much problem. It's always like that range. Of course, when you do a repair, you have to extend certain amount beyond that range. And another repair, like if you have a pier or abutment, which is like just one surface, you cannot go around it. What you can do is basically just provide like permanent, just anchor the steel plate into that, and it has holes. So you just have like a pump grout from bottom, so the water will come out, and later if you have like all the grouting material comes out, then it will be repaired, and just leave that steel plate as permanent form. For bearings, actually for steel member, bearing repair is very typical. In other words, most of bridges will experience a time that you need to replace bearings. To replace bearing, actually, a lot of people may just say, okay, cut off, because actually this bearing is heavily corroded, it cannot do much. You may just cut off the angle bolts and replace the bearings. But the problem is, once you cut off the angle bolts, you cannot drill a hole the same location as before, because there's still the angle bolts inside the concrete. So you have to drill a hole from a different location. And that's why typically you have to add a member to extend, like you may have to drill a hole from here. And when I do a bearing replacement, typically I try to using like elastomeric bearing to replace steel bearing. So elastomeric bearing is much cheaper and easier to be replaced in the future. And like this is another thing, like get damaged really easily. All this is caused by like water leakages. Like if you have this, you can just bolt another pair of members here. Okay. Yeah, another thing we have a lot of problem with like corrosion because there's stiffeners. I found that every time when you have a stiffeners heavily corroded, it's always required. Whenever you do calculation, you find like stiffeners is like typically required. So again, you may just like you don't usually weld it. You don't usually like weld steel plate back. So again, as I said, you typically try to. I think it's somehow. Okay, yeah, no. Yeah, you just try to bolt things back. Yeah, when you do a bearing replacement, typically try to jack the superstructure from where you have existing members. Like for example, if you can jack from abutment, that would be better. And it's very hard today. And so, if you don't have existing, when we design the new bridges, typically we will have to consider how this bearing will be replaced in the future. So we provide where the future jacking point is. And if you don't have a lot of older bridges that did not design that for, so what you can do is you have to provide temporarily jacking members. And these jacking members typically have to be put horizontal instead of following the deck. The deck has slope. So if we follow that and then you can jack, and as I mentioned, once you jack it up, you don't rely on that jack to hold the load. It typically provide we typically use a U-shape of steel plates. We just keep on steel shim plates and to hold. The jack is very it's almost like a pizza. It's about that size, only about that thin. So it jack up. So you don't need a lot of looms. So if you have a lot of looms, usually you need to provide another steel support. So in this case, it will be supported from abutment or piers. And sometimes if there's no loom to be supported, to support from abutment or piers, then you may have to have a temporary support. That is not desirable situation. And again, it's these are over piers. It's the same. Try to build. And another thing, typically, once you've done a bearing replacement, you just try to keep these members permanently. You don't need to remove that, so that next time if you need to do another bearing replacement, you can reuse that. And that's the operation. See, and also if you want to jack, of course you have multiple jacks. Try to have them connected together. So when you jack, it's jack simultaneously up. So that if you just jack one, and individually, sometimes you may have difficult to control the total force. And this is we call disc bearing. Disc bearing is just almost like plastic disc, which is very efficient way of provide support for large loads. So my preferred bearings is elastomeric bearing for small reaction forces, and disc bearing for big ones. People use pot bearing a lot. Sometimes I use too, but pot bearing is difficult to maintain. They have too many components. And calculations and when you design bearing, you need to calculate movement. So typically the movement should have three components. One is due to temperature changes, another due to shrinkage, and another due to creep. So a lot of people that design steel bridge a lot, and after they design concrete bridge, they forgot the shrinkage and creep portion, so that it's become the movement is insufficient. So that's what caused the anchor bolts damaged. Strengthening with a fiber reinforced polymer is that we mentioned a little bit earlier. The really big advantage is it's very, very high strength, and it has very, very good corrosion resistance. In other words, you don't have to worry about corrosion of itself. And the only problem it has is it does not have fire resistance. So that's why in the building structures, we don't use that much. But for buildings, for bridges, we typically don't worry about the fire resistance. That's why it's perfect material for bridges. Although it may have like a ultraviolet problem, it may not last like forever. Some people say it lasts forever, but it does not. But it will last much longer than your bridge. So we assume it will be last almost forever. So basically, I think another problem is that it's not really, it's not like a steel. So people can damage that easily. If you use like a very sharp, like a knife, you can cut it off. So that's why people were talking about using like a FIP material for cable-stayed bridges. And then people say, what if like a terrorist just cut them off? So that's become an issue. And the material property of FIP is like a very similar to steel. It had the difference is like actually I have comparison. That's a steel. Steel typically has linear like elasticity, and after yield, it has like a very much plastic zone. After plastic zone, it may actually enhance a little bit, but in general, we assume elastic and plastic. But for FIP material, it's almost like glass. It's just elastic only until it's break. So in other words, it does not give you any warning before it fails. So that's why whenever you use FIP material, you don't use at its ultimate capacity. You only use at certain levels. So the ACI will tell you like what allowable stress you should use. And also most manufacturers will give you recommendations too. So they may have different grade. So this is these E-modulus they are smaller than the steel. This is we call FIP. FIP is like a composite material. Basically, FIP is like a fibers. Actually, I didn't bring the material sample with me, but everybody can see. Basically, they are like a carbon fibers, but it's laminated into epoxy. So the large portion of the material is epoxy. So that's why once you become composite, the E-modulus is small, but the carbon fiber itself has even larger E-modulus than steel. But that alone cannot be used as construction material, so you have to use the composite. To do the design, actually, it's very, very straightforward. It basically just has two equations. One equation is for the strain, it's like a linear strain. In other words, in a cross section, all the strain should be linear, and the stress should be like all the compression in concrete, the force, and the force in tension basically assume there's a reinforcing steel and FIP. The total tension and compression force should equal. And the third equation is the moment arm of C to the neutral axis plus T reinforcement plus FIP each to the arm facing neutral axis. The total bending moment should equal to the external bending moment. And that equation should be able to give you basically the solution. But the only thing you need to check here that if you use that three equations, you have to check firstly, you will assume the steel yield. So you have to calculate to see that strain of steel to see if that exceeded the yield stress. If that does not exceed the yield stress, then you have to calculate back instead of using Fy, you have to use that strain times the cross section. So, and the E modulus, so you will be able to get actually force instead of if it's yield, the force has nothing to do with the strain. So that's a thing, one thing you need to check. The second thing really you need to check is you make sure that the strain of the compression fiber, the extreme fiber, does not exceed the allowable strain for concrete crashing. In other words, if concrete crashed here, which means you have over-reinforced here. That's just the same situation I discussed. I told you yesterday, one of my friends wants to repair his garage beams because he already reached that balance condition, so that by adding additional reinforcement does not work anymore. So if we have these three equations and checking these two conditions, then you will be able to solve all the problems. And of course, if you don't do that, you can follow, like ACI has a step-by-step equations. I'll show you later. Another thing FIP, fiber reinforced polymer, it does is for wrapping the column. I use that a lot. And once you do that, you increase ductilities a lot. And not only you increase ductility, like we know for concrete, once you have confinement, you actually increase like your compression strength. So this equation, like if you have circular and you provide the confinement, you will be able to increase the strength. But for rectangular, you also increase a little bit. But rectangular, even if you have a good confinement, because the shape, they don't provide as much constraint as the circular. That's why for bridge columns, we always tend to use circular column, or if you can. And for shear, like a shear is very much the same equation as we use for like stirrups. So you just treat that and the FIP material as like stirrups, very much similar equation. And there's a ductility increase. Like typically for concrete, it's like 0.4% is your maximum allowable compression strain. That's why once you reach that, you assume you've reached the balance condition. But if you have confinement for a column, for example, and you want to build a plastic hinge, for example, to build a plastic hinge, you need to have like enough like a deformation, and so that you provide very good confinement. And once you provide confinement, the allowable constraint, allowable like a string of concrete can be increased significantly. Again, circular is better than steel than rectangular. And for the bending moment, of course, it's just like that equation. That assumes you don't have any reinforcement. If you have reinforcement, you have other reinforcement component. But to get that, you need to do some calculation to see how much reinforcement you need using these like three equations. And of course, if you don't have to using all the three equations. If you can always do a trial, for example, if I provide that much FIP to see if they work. If not, it just increase and recalculate. And again, for the shear, like beam shear, it's almost the same as stirrups. And these equations are very straightforward. All these equations are in like ACI. ACI has a FIP design standard. And these are like, in order not to use, it's like an ultimate capacity. So these are the typically allowable stress, and this was provided by a manufacturer. And these are one of the manufacturers we use a lot. These are the typical installation procedures. Yeah, another is that FIP also can have rebars. And then the rebar, of course, the obvious advantage is that this rebar don't have corrosion potentials. But the only problem is now it's just more expensive than regular. And another problem is that because it's new product, not a lot of organizations are willing to be the first one to use. So everybody is relying I saw the manufacturer of these rebars. I talked to him. I said, "How is the market?" He said, "It's difficult to convince. Every time he goes to this Department of Transportation, they will say, who else is using?" He said, "No, I try to convince you to use first." He said, "No, I don't want to use first." But nobody just wants to use first. Right now, there are a couple of provinces in Canada being using that. And these are design examples. These are the step-by-step calculations. If you follow this step-by-step, you don't have to check these conditions I mentioned. Otherwise, if you use these three equations, you have to recalculate to see if you meet these two basic requirements. If you just do if you use a MathCAD, for example, you may just program these into these equations. So actually, that's a picture. That's in Toronto. Any questions? Now it's yeah.
How much is the difference in the cost of the FRP rebar with the steel?
Probably, I think about 3 times. I think actually they really don't compare with regular bars. Like in Canada, a lot of new bridges using stainless steel. So the stainless steel, and that's very much similar price. But people say, well, I know stainless much better than these, so I'd rather to use stainless steel unless you give me half price, I may change. If the same price, that's why it's difficult. In other words, the price is not low enough to attract people. Okay. No more questions? Yeah. Okay. Yeah, okay, just.
Okay, thank you. Good morning. One question about the FRP rebar. Which are the main benefits in comparison with the steel rebar?
And the main benefit is corrosion resistance.
That's the only one?
Very much only one, yeah.
Oh, okay.
And there's a lot of things that people tend not to use. One is there's no past experience. Although there's a lot of laboratory tests, a lot of research done by universities and research institutions, but there's not too many real bridges. And another thing that actually, because people cannot afford carbon fibers for rebar, that would be just too expensive. These are all glass fibers. And so the each modulus is much lower than regular, basically just regular reinforcement. People do use that a lot for tunneling operation. Like when you do tunneling, you need to have an entrance. Like if you have, it's very soft, it's difficult for the tunnel machine to go into that. So they build a reinforced concrete and reinforced concrete head wall. And so if you're using steel, it damages the quarry machine. So they use that can cut easily through. So in Canada, I talked to a couple of bridge owners, like a provincial, like a transportation department. They use that a lot for concrete parapets. They say that's not essential. They want to use that first to try out. Yeah, okay.
Good morning. I have a question about this strength. If you use FRP in bending moment, which would be, how can I say this? Which will be the limit for strength from bending moment using FRP? The same? It's not the same point.
The strain will be linear cross section. The stress will be the strain times the E modulus times the cross section. I mean the force. Yeah.
That's my question, because you have to calculate first how much strength you need to complete with the FRP.
Yeah. You need
So
to know
but you
the
have to know
strain.
the limits that that the product has. So that's my question for you.
Yeah, and like a reinforcing steel beam design, because reinforcing steel has like very short strain before it reaches yield. So we always assume it's yield. So that's why you don't calculate a strain or stress, because you assume yield stress. Before that, it's never yield. So you need to actually calculate what the strain is to be able to calculate force. And once you calculate what strain is, then you just look at to see if it's exceeded the allowable strain, because if it's too high, it's not allowed. Then you need to add more to break down, to lower the strain, and then use that as a new calculation to get the force.